Hello friends, in the previous lecture we studied the radiative heat transfer between black surfaces. Now in today's lecture we will study radiative heat transfer between grey diffuse surfaces. Just by converting the surfaces from black to grey, the problem of radiative transfer becomes much more complicated. As we will see in the derivation of mathematical expressions, the problem involves not just algebraic equations, but rather integral equations. So, this class of problem is significantly difficult to solve as compared to the radiative heat transfer between black surfaces. So, diffuse grey surfaces, we have already studied the classification of the surfaces. Diffuse, as we have already studied, means it emits and absorbs radiation equally in all directions. That means epsilon lambda prime is equal to alpha lambda prime is equal to epsilon lambda is equal to alpha lambda. So, this is a diffuse emitter and absorber. The emittance and absorptance does not depend on direction, it is uniform in all the directions, and the surfaces are grey. That means the emittance and absorptance do not depend on wavelength also. So, we have emittance as equal to epsilon and absorptance as equal to alpha. They are equal as per Kirchhoff's law, but they do not depend on direction or wavelength. So, this is we called diffuse grey surfaces, and this epsilon and alpha is not equal to 1. If it is equal to 1, then it will become black. These surfaces are rather called grey. They have emittance and absorptance value not equal to 1. Okay. So, when we have emittance not equal to 1 or less than 1, the amount of energy emitted by a surface is simply epsilon times the black body emissive power EB. So, this is the amount of energy emitted by a surface. Okay. This is going to be less than what a black body would emit, and the amount of energy absorbed, if let us say H is the amount of energy coming in falling onto a surface, then the amount of energy absorbed is simply alpha times H. A black body would have absorbed all the radiation, while the grey surface absorbs only a fraction of the incoming radiation, and this fraction is called absorptance alpha. So, we define, so part of this radiation H is basically absorbed, alpha H is absorbed, and rest of it 1 minus alpha H is basically reflected back. So, we define a quantity called radiosity J as the sum of energy emitted by the surface and also energy reflected by the surface. So, the total amount of energy leaving surface is basically defined as the radiosity. So, it contains contribution from emission and it contains contribution from reflection. Okay. So, the first quantity definitely depends on temperature of the surface. So, this will depend on the temperature of the surface, and this quantity depends on temperature of the source from which H is coming. Okay. So, these two are different in the sense that the temperature of one surface may be significantly different from the other. So, one value of the energy emitted will be in one spectral range and the other value may be in different spectral range. So, amount of energy, if somebody is interested in looking at the structure, the spectral structure of the radiation, then this may look like this. Okay. If you look at the amount of energy emitted versus wavelength, okay, you will have this kind of structure where this could be the black body emissive power at temperature T, and this could be the spectrum for H at the source temperature. Okay. So, they may be spectrally different regions, okay. But for this calculation diffuse gray, the epsilon and rho or alpha are independent of wavelength, while the black body emission power EB and irradiation H will depend on the temperature of the respective surfaces, and definitely they will depend on wavelength, okay. So, we write energy balance for a surface dA, we take an enclosure just like we did for the black surface, okay. It may have some opening from which external radiation may come in, okay. Let us say we have a small element here, okay. Let us call this dA, okay. So, the total energy balance for this surface dA includes the energy emitted from this element, that is emittance times the black body emissive power at that location, minus energy absorbed. Now, energy absorbed is equal to absorptance alpha times total irradiation H. Now, this total irradiation H may include radiation coming from the entire enclosure as well as radiation coming from outside H naught, okay. So, it can include both the components. So, now we will further simplify this equation. The same heat flux on this element dA can also be written in terms of radiosity. So, radiosity is defined as total energy leaving the surface through emission and reflection, and it is J, and minus H, H is total irradiation. So, this is total energy leaving and this is total incoming energy, of course radiative energy, okay. And this is total emission and this is total absorption, okay. So, we can write heat flux in terms of either black body emissive power and irradiation or radiosity and irradiation. Now, we have total irradiation on surface dA HR dA as contribution from the entire enclosure, just like we did in the case of black body. So, we take view factor from dA prime, let us say dA prime is a small area on the enclosure and we have to integrate over the entire enclosure. So, we multiply by dA prime. So, we take the view factor between these two surfaces, and J r prime is the radiosity from this element dA prime, okay. So, this is the total amount of irradiation plus irradiation from the component coming from outside the enclosure, okay. So, we substitute this value of irradiation, okay. Before we do that, we simplify as we did in the case of black body enclosure. We write dF dA prime to dA times dA prime as simply equal to dF dA to dA prime dA using the reciprocity theorem. So, we substitute in this equation and we cancel out dA from both the sides. So, we get the expression for irradiation, this is called irradiation at location of the small vector dA, radiosity integrated over the entire surface multiplied by the small view factor plus outside irradiation, okay. So, we substitute this expression in the expression of heat flux and we get this expression. So, QR is equal to the energy emitted by the surface and energy absorbed by the surface, okay. So, this is how we can calculate the heat flux for a diffuse gray enclosure. Now, the difficulty in solving this expression is that it includes an unknown quantity radiosity in this integral equation. This type of equation is called integral equation and we have an unknown quantity J coming into this integral. So, first of all we have to solve for J and then we can find out heat flux. So, what we do is we use the same expression, okay. So, what we do is we use this expression, okay, this equation we use, okay. From this equation we can solve for the radiosity J, okay. So, radiosity can be written in terms of epsilon r EBr minus alpha r HR, and taking the HR on this left hand side we can solve for radiosity. So, so using that relation we can solve for the radiosity. The radiosity at any location r is equal to emittance times the blackbody MSE power plus the reflected part of the radiation and outside radiation. So, what we have just done is basically substituted the value of H in this relation. Okay, we have substituted the value of H in this relation and solved for Jr. Okay. So, once we solve for Jr we get the results for radiosity. Now, if on any surface the heat flux is specified rather than temperature, let us say there is a surface out in the enclosure or some element in the enclosure for which the for which the temperature is not known, rather the heat flux is known, then we can write down the radiosity in terms of heat flux also from the same equation. Okay. So, from the same equation the radiosity is simply Q plus HR. Okay. So, Q plus HR, the irradiation. So, we can solve for radiosity using these two expressions. This is for known temperature and the other expression is for known heat flux. But the problem is still not solved. Why? This is not a normal equation. You cannot solve for radiosity just like an algebraic equation, because we have radiosity appearing on the left hand side, but we have radiosity appearing on the right hand side, and that too under an integral. These type of equations are called integral equations and they are not easy to solve. Okay. So, it is very difficult to evaluate these equations because these are integral equations. So, unless and until we simplify, do some simplification, it is very difficult to solve. Okay. Now, how do we solve it? So, we basically write down the expression from previous. We take the same expression, Q is equal to this expression, we take Q is equal to epsilon EB minus alpha H, okay, and subtract the heat flux again multiplied by alpha Q. So, we solve for Q minus alpha Q. Okay. This gives us epsilon EB minus alpha H, and minus in this Q we put for J minus H. Okay. So, from the same equation we are just trying to manipulate, okay, and this simplifies to epsilon EB minus alpha J. Okay. So, from this we can solve for heat flux Q is equal to epsilon upon 1 minus epsilon EB minus J. Okay. So, this is the expression for the heat flux. Okay. Or in terms of heat flux we can solve for radiosity J is equal to EB 1 upon epsilon minus 1 Q. Okay. So, from this our problem has greatly simplified. What we have done is we have found a solution for radiosity which was appearing in the integral equation, okay, in terms of heat flux. So, our objective is to eliminate radiosity, because in calculations radiosity is not our objective is the heat flux. So, what we have done is we have written radiosity in terms of heat flux, okay, by manipulating the governing equation of this problem, and once we have radiosity we will substitute it back in the governing equation to calculate the heat flux. So, when we put it back in this equation, okay, so this is the equation for heat flux. Now, we have calculated J in for heat flux, we will just put it back. Okay. The nature of the equation is not going to change, okay, the nature of the equation will remain integral equation. Okay. This is something you cannot simplify as compared to the black body radiation, where we did not encounter this problem of integral equation. The integral equation is inherent for gray problems. Okay. So, this problem will remain, and our equation now in just Q as a variable reduces to now Q upon epsilon minus this integral term plus outside radiation is equal to EB minus EB r prime df dA dA prime. Now, this is not a unknown, I mean you can easily calculate this last term, because EB is known to you. If you know the temperature of the surface, you know the term and you can easily integrate it, but this term is not easy to calculate because Q is a variable and it is appearing inside an integral. So, this is an integral equation. Okay. So, let us see how we can solve problem of this type. Okay. So, just like we did for the black body enclosure, what we will do is we will break the enclosure into a number of flat surfaces. Okay. Let us say n surfaces we will break. So, this is going to be our first simplification. Okay. So, this is A j, where j varies from 1 to n. So, we have divided the enclosure into n flat surfaces. Okay. When we do that, we also assume that the radiosity is uniform over a surface. Okay. This is just like an assumption we make in the black body case, where we assume that the temperature is uniform over the surface. So, here we are assuming radiosity is uniform over the surface. Okay. So, this equation, the value of EB can be taken out. Okay. The value of EB can be taken out, it is independent of the location, it is just a variable for a given surface. Okay. And then we have summation over all the surface, the view factor from a surface di, let us say this is surface I and this is the element di. Okay. So, we are calculating the view factor f di to j as per the argument that we made in the case of black body, that the view factor is not uniform. You can have radiosity uniform, you can have temperature uniform over the surface, but you cannot have the view factor uniform over the surface. You can have an average view factor, but not a uniform view factor. So, first of all we will assume that the view factor varies over the surface. So, we just left with f di and j, okay, and minus the incoming radiation. Okay. Now, we will take the average. So, what we will do is we just take an average over the surface A I over this surface. This is the average heat flux, on A I, okay, average emissive power. Then this is view to factor between finite element areas A I and A j. Okay. Again this is going to be an average of the small element view factors, and then average value of the irradiation. Okay. So, this is the first expression basically what we have got. Okay. Okay. Now, we have another expression again coming from the same relation. From this relation we have this another expression for Q. Okay. So, Q is equal to epsilon 1 minus epsilon EBI minus JI. Okay. Now, this expression we have to basically find out. What we have to do is eliminate J between these two equations. This is the same exercise that we are doing we did for the integral form of the equation. Now, we are just doing it for the summation, okay, because we have divided the enclosure into many surfaces. So, we have to eliminate Ji between these two equations, and once we have, what we get is basically an equation in just heat flux. Okay. So, we have eliminated using this equation, substitute the value of Ji into this expression, okay, in terms of Qi, okay, and what we get is basically this kind of equation. Okay. So, Qi upon epsilon I from this this term, okay, Ebi, and then we have substituted for the Ji in terms of Q, and we have taken it on the left hand side. So, this is our final equation. Okay. So, for gray surfaces this will be used as the equation to solve for. Okay. This is the first form for radiative transfer between gray surfaces. Okay. We have finite number of surfaces in an enclosure, all are gray, and this is the first form. Now, second form as we derived in the black body case, we write Fij as per the summation rule, and we can just write it as equal to Ebi Fij summation over j is equal to 1 to n is equal to Ebi. Okay. So, we substitute for Ebi using this expression, and we get this relation in terms of the difference of MSC power of the two surfaces. This is the second form. Okay. So, the two forms we derived earlier also, now we are basically deriving the same. This is the second form. Okay. Now, let us see what happens when we substitute epsilon is equal to 1 in this case, that is the surfaces are black. Okay. I will just use this equation. So, in this equation let us put epsilon I is equal to epsilon j is equal to 1, we get q I. This term will reduce to 0 because 1 minus 1 is equal to 0, plus h naught I is equal to summation f I j E b I minus E b j. Okay. And this is same as for the black enclosure that we derived in the previous lecture. Okay. So, just by substituting the epsilon value equal to 1, this relation has reduced to the same relation that we derived for the black enclosure. So, these two equations we will use to solve for radiative heat transfer in a gray enclosure. The enclosure is divided into a finite number of surfaces, j is equal to 1 to n. Okay. So, let us solve one problem. We have two isothermal gray concentric spheres. Okay. The inner sphere has radius of r1 and outside sphere has radius r2. The temperature of the inner sphere is T1 and emittance is epsilon 1. Outside sphere has temperature T2 and emittance epsilon 2, and everything is uniform. Okay. So, we have to find out radiative heat flux between two spheres. Okay. So, let us solve this problem. So, we will use this equation. Let me just write down the equation first. So, this equation we are going to use. So, the equation we will use is q I epsilon I minus summation j is equal to 1 to n 1 upon epsilon j minus 1 f I j q j. There is no h naught I, so we will just ignore it, and then E b I minus summation over j is equal to 1 to n f I j E b j. So, this is the equation we are going to use. Okay. So, surface 1, that is the inner sphere, we write q 1 upon epsilon 1 minus 1 upon epsilon 1 minus 1 f 1 1 q 1. So, here f 1 1 is not going to be 0. Okay. So, this is the sphere. We will see if f 1 1 will be 0, it is a convex surface. F 1 1 q 1 minus 1 upon epsilon 2 minus 1 f 1 2 q 2 is equal to f E b 1 minus summation j is equal to 1 to 2 E b j. Okay. Or this can be just written as f 1 2 E b 1 minus E b 2. Okay. So, this is for surface 1. Then similarly for surface 2, we have q 2 upon epsilon 2 minus 1 upon epsilon 1 f 2 1 q 1 minus 1 upon epsilon 2 minus 1 f 2 2 q 2 is equal to f 2 1 E b 2 minus E b 1. Okay. So, now let us look at the view factors. So, f 1 1 definitely is 0. Okay. F 1 2 is going to be 1, then f 2 1 okay, is equal to by A2. This is from the tables. Okay. So, we can easily calculate the view factors. So, F21 is A1 by A2 and F22 is equal to 1 minus F221 is equal to 1 minus A1 by A2. Okay. So, this is how we have calculated the view factors. Now, let us simplify the equations. So, we have q1 upon epsilon 1 minus 1 upon epsilon 2 minus 1 q2 is equal to sigma T1 power 4 minus T2 power 4, and 1 upon epsilon 1 minus 1 A1 by A2 q1 plus 1 upon epsilon 2 minus 1 upon epsilon 2 minus 1 minus A1 by A2 q2 is equal to minus A1 by A2 sigma T2 T1 power 4 minus T2 power 4. Okay. So, this is how we have basically written these two equations. Now, we have to solve for either q1 or q2. So, we can eliminate either q1 from this equation, or we can eliminate q2 from this equation. So, let us eliminate q2 from this equation. Okay. So, and we will solve for q1. So, we get q1 is equal to, and this is going to depend on the areas of the sphere. So, we have sigma T1 power 4 minus T2 power 4 upon 1 upon epsilon 1 plus A1 upon A2 1 upon epsilon 2 minus 1. Okay. So, this is basically the expression for the heat flux. For black enclosure, now just note down that q1 should reduce to the black body relation, that is q1 should be equal to sigma T1 power 4 minus T2 power 4, okay, for the black enclosure. So, let us put epsilon 1 is equal to epsilon 2, the second term in the denominator will be 0. Okay. So, we just get q1 is equal to sigma T1 power 4 minus T2 power 4. Okay. So, this is for the black and this is for the gray. Okay. So, now one can find out the magnitude of the denominator and see what is the effect of this gray emittances on the heat transfer between the two spheres. Okay. So, just to see the effect of the gray emittances, let epsilon 2 is equal to 1. So, that the second term is 0, okay, and let us say epsilon 1 is equal to, let us say 0.2. Okay. So, we get q1 is equal to 0.2 sigma T1 power 4 minus T2 power 4. So, this has reduced the heat flux from the surface 1. Okay. Similarly, we can put epsilon 1 as 1 and take a value of epsilon 2 and find out what is going to be the effect on heat flux. Let us do another problem. Okay. In this problem, we have a collector, okay, a solar radiation collector plate. The temperature of this plate is 350 Kelvin. Okay. Now, we want to improve the efficiency or performance of this plate by putting a vertical highly reflecting plate adjacent to this plate. Okay. So, this is called reflector, okay, and this is collector plate. Okay. So, collector plate has emittance which is equal to epsilon 1 equal to 0.8. Okay. That means, it is not a very good reflector, it is a good absorber. On the other hand, we have put a vertical plate adjacent to it which has epsilon 2 emittance of 0.1. It is not a very good emitter or absorber of radiation, but its reflectance is very high, that is 0.9, 1 minus epsilon 2 0.9, and it is diffuse, both surfaces are diffuse, and by putting this reflector we assume or we expect that some amount of radiation falling onto the surface will be reflected towards the collector plate and the amount of radiation received by the collector plate should increase. So, let us see how to calculate this problem. Okay. So, we will use the similar method that we basically used in the previous problem. So, we will use the same relation, surface 1 we will write the heat flux. Okay. This is our surface 1 A1. Okay. So, I write this energy balance EB1 minus F12 EB2 is equal to Q1 upon epsilon 1 plus Q sun cos theta, where theta is the angle made by the solar radiation from the vertical direction. Okay. And surface 2 similarly we write F21 EB1 plus EB2 is equal to minus Q1 plus Q sun sin theta. Okay. So, solar radiation is falling on both the surfaces. Okay. It makes an angle of a projection of cos theta on plane 1 of surface 1 and sin theta on the vertical plate. Okay. Now, what we are basically interested in is the amount of flux on surface 1, Q1 we are interested in. So, we will eliminate and Q2 is given 0, this is insulated. So, the reflector plate is insulated. So, Q2 is 0. So, we eliminate EB2, the temperature of the reflector plate is not given. So, it is a variable, but we do not need it. So, we eliminate the variable EB2 from this equation and we solve for Q1. So, we get Q1 is equal to 1 minus F12 F21 Q sun cos theta plus F12 sin theta. Okay. 1 upon epsilon 1 plus minus 1 upon epsilon 1 F12 F21. Okay. Now, the view factors are easily available from the book. Okay. For two plates perpendicular to each other, we can calculate the view factors. The view factors values I am writing F12 is equal to 1 by 4 and F21 is equal to 1 by 3. Okay. It depends on the areas of the two plates. Okay. So, F12 is 1 by 4 and F21 is equal to 1 by 3. So, substituting these values and the values of temperature and emittance, we get Q1 is equal to minus watt per meter square. Okay. This is the amount of radiation received by the surface, the collector plate, okay, by direct absorption and by reflection from the reflector plate. Okay. So, we have discussed the radiative heat transfer between gray surfaces. In the next lecture, we will study the method of network and we will try to solve these problems, some more problems on this topic using the network method. Thank you.